So I'm going to be talking about democratizing NLP content modeling with transfer learning using GPUs. So one of my colleagues, when he saw the title, he was saying, why do you want to put using GPUs in the title? And I don't have any specific slides to say why using GPUs, but it kind of goes into the theme of democratizing NLP in the sense that there will be some work that will be built using GPUs, but later on the idea is that anybody who does not have access to GPUs or probably even doesn't necessarily know how to build a deep learning model on GPUs could use the results. And that's the role. So before I go into any technical details, I'd like to kind of introduce what is Chegg. And that's important to understand the talk overall and why some of the decisions are the way, decisions are taken the way it is. So this is like our main website. We are a student hub. We cater to students and provide them help in all possible directions. Some of the ones you can see here are textbook rentals, and I will go into more details about study, math solver, as the name suggests. You can go and solve equations in it. Tutors, I will again go into some details. Writing is another product which basically gives you writing help. It helps you build bibliography, but also gives you suggestions if your grammar is wrong, so that kind of a product. And internships is another side where basically students can come and apply for internships. So it's like the whole package in your student journey from the beginning to finding a job in some sense. So let me go into some details into Chegg Tutors. And this is a product that I have spent most of my time working on. It is online tutoring on demand. So a student comes into the site, goes in, and basically here you type the subject you need help with. You click find me a tutor, a box opens up. In the box, the students are strongly advised to give as details about the questions as possible. Sometimes students will say something like, please help me, I have an exam tomorrow. Those are really hard to work with, but a lot of the times they will give the details of the problem they're working on. Another product we have is Flash Tools. As the name suggests, these are flashcards. This is a company we acquired recently. Some of you might have used Quizlet, which has a lot of flashcards. This is similar. And the idea here is, again, you go and you type in a term that you're trying to learn. What is metaphase? And then you can either create your own cards, but there are also cards that are already existing. A lot of students would prefer to find cards that are already existing to study for their exams. And it has like a wide range of subjects. And finally, the product that is like most popular in some sense is Chegg Study, where you can go and ask a question. It could be from a textbook, but it could be also a question that you are asking. An expert on the other side would go and answer your question. And in this case, like the question is about classical thermodynamics. What you will realize is that this is like the data that I am working with. Chegg is mainly a portfolio business. These are like, each of the product are like a different teams with different engineering teams distributed across the globe. So sometimes being able to democratize anything is like very useful at our company. So a brief overview of what I'm going to talk about. Democratizing NLP, I'll keep coming back to it throughout the talk. Transfer learning, I'm going to talk about Vertivec, which probably most people have heard about, more on sentence and character embeddings, and finally something that's very popular now, word embeddings in context. And finally, I will go into some applications. One of the applications that we have a lot of success with is knowledge-based creation, which kind of refers to tagging concepts onto the content that we have. It could be flashcards, it could be questions, answers to questions, some dialogue happening between tutor-student chat. It could be anywhere. So what do I mean by democratizing NLP? Well, we have a lot of text data. The first goal is to give some structure to that text data. If you have a lot of text data sitting somewhere, it doesn't help you in any way unless you can query it in some form. So one goal is not just data scientists, but data analysts should be able to query the data and get some meaningful results out of it. For instance, one of the product managers once asked me in tutors is, how many students are asking tutors about how does the product work? Because, tutoring is an expensive platform. We would rather have like a QA system, support system that answers that question rather than students actually asking the tutors that how does the product work. So these are like very analytics kind of questions which should be easily queryable. And another very important part is there may be machine learning practitioners. And when I say machine learning practitioners, I also mean not people who probably don't have a very deep knowledge in machine learning. Maybe they have like the pipeline with Spark or any other distributed system, and they know how to use like logistic regression, use some features, use logistic regressions, and get some predictions out of it. So even those teams should be able to take advantage of the rich information that's there in text data. So why transfer learning? So transfer learning gives structure to unstructured data. So it converts texts into vectors. It can be used to solve a range of problems like summarization, entity recognition, tagging, keyword extraction, but also any other specific downstream problem that you might have. And another really nice thing about transfer learning is that it is doing auto-featureization of your text. That is, as an NLP engineer, a lot of the times you kind of have features like, do I have the word we in this text? And then that becomes, and this is very specific to saying we, you could have like a list of words. But these are, you don't have to do that kind of specific feature engineering using transfer learning. So this is a traditional NLP pipeline, and in some sense a traditional machine learning pipeline. Initially, you invest in collecting data. Luckily, we are in a place where we are collecting data for all of our products in a lot of details. And data can be in the form of structured data, in the form of text, in the form of images. And the next step is gathering label data. So you go to annotators and you ask them to label whether your data is of the type you want. Gathering label data is a very expensive step. And that is one of the reasons why I'll talk about like what do you do when you have small data. And then a lot of feature engineering. Feature engineering could be as simple as doing TF-IDF or bag of words, like just counting words. But it could also be very complex domain-specific things where you look at certain occurrences of part of speech, for instance. Is there a noun followed by a verb? That kind of work. And then finally, you fit a model. It could be a logistic regression or an SVM or something more advanced. So using deep learning, people do get rid of a lot of feature engineering, which is great because it takes a lot of time to do detailed feature engineering. But general deep learning problems require a lot of data. In most real situations, especially when you're starting a problem, you don't have a lot of data. And it's very hard to go and justify and say, hey, I need to collect 10,000 data points, where maybe each of your data points, it takes 5 minutes to annotate it. And in our case, because this is like academic material, you need someone who's an expert in chemistry. You need someone who's an expert in biology to actually spend 5 minutes over a question and an answer and say, give more information about it. So all project starts with very small data. So what is transfer learning? So you start with, in the realm of traditional machine learning, where you have task one, you have some kind of domain, you do all of that, build a model, you have some results. In the other domain also you repeat the same thing. And you don't necessarily learn from one task to the other. In the domain of transfer learning, you learn in one domain and you gather that knowledge, you store it in some form, and then you feed it to model 2 to make predictions in the other domain. And the advantage here is mainly that in domain 2 you might have very little training data, whereas in domain 1 you might just have a lot of training data because of how the problem is set. So classic example of transfer learning is computer vision. In computer vision, transfer learning has been used in much details for a while now. Especially like the ImageNet models probably started coming up a few years ago maybe. 5 years ago or 6, maybe more than that, 6 years ago. So there had been like a set of images which was a basic classic data set which everybody could borrow from. And this particular example, it is one of the Kaggle competitions where the problem was to identify diabetic retinopathy, and a lot of the models used the ImageNet's pre-trained features and applied it to something so different. So the features would be trained on flowers or cats or something completely different, and they would generalize to diabetic retinopathy, which is like a very different field. It has been used in fields of video recognition, human pose detection, and other types of small data. And in some sense, the field of computer vision is way more advanced in the transfer learning phase compared to natural language processing. So I will start with like this in transfer learning. In NLP I will start with the simplest example of word2vec. So how many of you are kind of familiar with the slides? You have looked at. Okay, so most of the room, you know what's going on. In the realm of word2vec, you have this example where if you do king plus queen minus man, you get a woman. Basically, you have all the vectors which are contextualized based on the text. And it's a very shallow network. It's basically one layer, and then you have a softmax. You try to predict the next word or something else, but basically your weights come from just one layer. This has done pretty well. Yeah, and in order to use word2vec, one thing you can do is just download Google's pre-trained vectors. For a lot of domains, especially for domains like where students or customers are asking for how does this product work or other kinds of support, something like pre-trained vectors work really well. But for a lot of the problems that I work on, it's specifically dealing with details in algebra or details in physics. And for them, a lot of the times I would train my own vectors. And even that process, I mean, the word2vec came out about 5 years ago. There's TensorFlow, there is like other, there's GenSim, and then there are all of the other packages have like some form of word2vec. You need like so few lines of code, like this is probably less than 10 lines of code to even generate your own word vectors, which is very convenient. And as I go through the next parts of my talk, I would really like to mention that even though the next things are interesting and they are bringing newer results, this is so easy that it's still very much used in different parts of our pipeline and used by a lot of people. So the next thing I will go into is character embedding. And character embeddings are kind of important because a lot of the times your data you might have a lot of unknown terms, which happens very often when you have the language of students. Like for instance, in the first slide when I introduced Chegg, the sentence was everything is figureoutable. Figureoutable is not, and that was specifically geared to its students. It's not something you would find in pre-trained vectors, but it's also hard to, there's just new kind of language that's hard to always vectorize or hard to find in your vocabulary. So the nice thing about character embeddings is it starts with characters, but eventually goes to, it's eventually able to represent syllables or parts of a word, which makes it less prone to new or unknown words or new symbols even. Like when we are dealing with algebra or other parts of math or even chemistry, there are different symbols that come in which we might not always have stored. So this is a very typical character embedding pipeline. Here you take all of the single words and then you have some word embeddings. You apply another convolution layers with multiple filters. That gives you like a tensor-like format for the output. And then you can do something like max spooling over time, or you can do something else as well, but you finally get like a 1D vector. You pass it through an LSTM, And it doesn't have to be one LSTM, it could be layers of LSTM depending on what you're trying to do. And then finally you have a softmax layer, you keep running this, and you kind of fill up the, as you optimize for the problem you're trying to solve. If it's a language model you're trying to solve, given play, is the next word premiered, you will eventually fill up the character vectors of play. And I'm bringing this up for two reasons. One, we have used it in several cases where it has shown better results than pure word2vec, but also because in general this can form a very good first layer to, like, your character vectors can form a very good first layer to another downstream stream task. These are things I have kind of discussed. One of the advantages here that I have not discussed is that because characters are kind of few, if you were just considering the English language plus a few special characters, your initial one-hot encoding could be just 100, could be just 100 in one dimension, whereas if you were doing it with words, it could be 10,000, which means the initial vector is huge. Of course, character embeddings do require deeper networks, so that part is also there. I guess here is where using GPUs also kind of comes in a little bit. Once you start doing your own embeddings, you will be storing them somewhere, which can in later phases get used by other people who might or might not use GPUs. So next thing I will look at is sentence embeddings. This is also something we built in-house, both the character and the sentence embedding we built in-house just because it was more relevant for the data that we had instead of downloading data. For sentence embedding, I think TensorFlow has good pre-trained vectors, which again work in generalized domains quite well. So the different architectures that I looked at was autoencoders, where you take the same sentence and on the other side you try to reproduce the same sentence, and you have a structure in between, part of which is your sentence vector. As you keep doing like the cross entropy through the keep decreasing the cross entropy, you fill up your you basically change the weight of your sentence vectors to represent the problem. It's similar for language models. You try to predict the next word, and for skip thought vectors you try to predict the previous sentence and the next sentence given the current sentence. I will take a brief look into the architecture of the sentence embedding form. So in this particular architecture, the initial input was the tensor of the word vectors. It was fed into an LSTM, which outputted your sentence vector, which was fed into a softmax. And then the problem we were trying to optimize for autoencoders was the same sentence itself. For language models, we were trying to optimize the next words. Any questions so far? Okay, cool. So the next slide I'm going to go to is thinking of word embeddings in context. So I will just read through this comic. So the morning air is getting crisp. And then the reply, the other person says, wait a minute, 2 months ago it was all about getting burnt to a crisp. Probably talking about California, but and then the next thing he says is, how come no one gets burnt to a crisp in crispy air? Or once in a while the language model comes unraveled, snap, crackle, flop. But we see this in many different examples, like somebody is very good at playing the piano, and then in another sentence the child is playing in the park. You have the same word, but they mean something completely different. So if you have the typical word-to-vec representation would have the same vector for both of them. So in the new system, what you want is you want the vector of crisp given the context. And I started looking into this very recently, and there is this paper on deep contextualized word representation, which got the Best Paper Award at NAACL in 2018. So the nice thing, there are several papers in this space. One of the nice things about this formulation is that the codes are publicly available in Allen NLP. Initially it was just in the PyTorch framework. Now there is availability in TensorFlow, Keras, and Chainer. So you could basically download it and start working with it without worrying much. I will go into a little details of how does it work. And I have again repeated the character embedding slide mainly to point out that the input to Elmo is the character embeddings similar to this structure. So the first layer is a character embedding, and that goes into Elmo. So how does it actually work? It uses a bidirectional language model, which means it maximizes the probability given play, given the Broadway, what is the probability of seeing play, and plus given premiered yesterday, what is the probability of seeing play before it. So it maximizes both of these probabilities. So that's one thing that's different compared to previous language models that I have discussed. The other thing is the outputs it represents are also a little different. So one obvious output that it gives is the last layer. So this is the information from the last layer of the embedding. But it also gives the information from the other layers of the embedding. And what the authors have seen is that for some problems which are syntactic, like detecting parts of speech, lower layers are more useful. And for other problems which are more semantic, like differentiating between play in the context of playing music versus play in the context of playing in a park, the upper layers are more useful. They also kind of outline a way to use all of these layers with a regularization factor, which is quite interesting. So before I go into this also, the way I have used, maybe I should stay in this slide, the main ways I have used this output is I've used max pooling, I've also used aggregating, and I'm looking into some other, max pooling and basic averaging of the layers, and the last layer of course, and I'm also looking into some other techniques of using all the layers correctly. I have not used weighting each of the layers differently and figuring out the weight from the problem at hand yet, mainly because most of the problems I work with are in the realm of very small data, so it's hard to figure out weights if you have too small data. So this, I say then, but it's still true now, this used to be the traditional transfer learning pipeline. You get like initially you have some sentence going in, you have some embedding method, you have a vector representation, and you have a downstream classification task. With something like context aware outputs, what you can do is you have, so this is something that would come out of Elmo. You have the initial text, you have the embedding method, you get the information on all the layers, and then you can fine tune each of the layers depending on the specific problem that you have. This is actually fairly common in computer vision. People, when they take different layers of ImageNet to do predictions, very often they will change the layers with some neural architecture to make the prediction. So it's something that's almost being borrowed from computer vision. And then the next step is aggregating. Very often, so for instance, I have not had a lot of success with fine-tuning, and it's not because it doesn't work, it's mostly because I did not have enough data that gave me enough information to change the vectors to make a difference. But aggregating is something that almost everybody would use because you have so many layers of information given to you, you have to decide how you want to choose it. And then there are many different kinds of aggregation. So if I had to sum this up in like one slide, the whole process of transfer learning, initially there is the training process. If you're using something like Elmo, you get a lot of it out of the box. Another thing I would say about Elmo is because it uses character embedding, it was much more suitable to the type of data I had, whereas Word2Vec out of the box would not basically have a lot of the tokens that I would have in my vocabulary. You can have language models, machine translations, either you do it in-house or you just get it pre-trained. The next step, which is less pursued in NLP, is use some neural architectures to change each of the layers. It could be RNNs, CNNs, or the transformer model. which I haven't spoken about much. And then the final thing to do would be aggregation, which could be an averaging or a max pool. Recently, people are also looking at attention models, which will dynamically allocate weights to the different layers. I also typically show this slide because this is my pipeline where I mainly get the training, aggregate, and then do the classification on top of it. Having said that, I'd like to show some information on like performance from model tuning. So this is from a blog from a company called Indico, and they have a framework where you can go and benchmark your transfer learning vectors against their data. And they have shown that as you have more and more training data, fine-tuning the vectors gives you more information. I think this is useful, and this will be used more and more as this paradigm becomes more, how should I put it? As this becomes more normalized in some sense, or more standardized, like people actually know what are the best ways to tune the layers before going into aggregation. So I'll talk a little bit again about democratization. So far I've mainly spoken about how do you build the vectors. So having transfer learning, anybody can take advantage of deep learning even if they have small data. Again, feature engineering is kind of taken care of in this space. And also like this, once you have the results, you store it in Redshift or anywhere else where any remote team around the world could pull the data and create a model without knowing much. So before I go into applications, any questions? Yes?
Maybe I'm not quite following, but it seems like the examples you're describing are a one-to-one mapping of a single word to some vector representing the meaning of that word. How does that address the problem, though, of that word having a different meaning depending on its context?
So maybe I should have put an output of the. I probably don't
the same vector
have. I do not have necessarily. I should have put a slide on the output. What happens is you have this sentence: the Broadway play premiered yesterday. The output, even for a single layer, would be a tensor, which would represent would be a word vector, but it would be a tensor for this sentence. So play, let's say you have another sentence which is the boy is playing in the park. That would be a different vector, like that tensor representation would be different.
Right.
So you would have to give the entire sentence, and the output vector would be one set of numbers. You give another sentence, which is the boy is playing in the park. Your output vector will be another set of vectors. So if you look at play in sentence 1 and if you look at play in sentence 2, the word vectors are different. And they are different because of that particular context. Does that make it somewhat?
So you're generating an embedding for the sentence or the word or for both?
It is directed towards a sentence. So the final output is, it could be more than a sentence. You could put 2 sentences in it as well, but it is mostly optimized for a sentence. So you put in a sentence and you get like the word vectors out of it. And maybe we can talk about it more. So in the space of applications, the first thing I'll talk about is creating a knowledge base, which we've been quite successful with most of our data. The other things we are looking at is finding unique concepts, and in some applications it's particularly important. And the ones that are in gray are things that are more in progress or things we are sort of exploring with different kinds of techniques. And some things here like auto-creating flashcards would be like a really good product application for us, or helping tutors or expert answerers with relevant material. These would have quite a bit of impact. So what do I mean by creating a knowledge base? So we have all of the contents. At one level, we have the different subjects. It could be algebra, physics, statistics, mechanical engineering, and so on. And we have several tens of subjects. Then within each subject, you have like further drilling down. So you let's say I go into statistics. You have some high-level clusters, probability testing, regression, and then you keep going down there. Keep going down inside discrete probability distributions. You can go down binomial Poisson or discrete probability distribution. So basically, you create a knowledge tree, and then you tag all of your content with different nodes in the tree. In some cases, this has been treated as a multi-class problem with regular like classification. So the typical pipeline that we followed was you get the sentence embeddings from the pipeline that I showed. You concatenate the Elmo embeddings, and that requires some aggregation before you concatenate it. We add a TF-IDF weighting, and that is very specific to the data type that we have. A lot of the times we do get repeatedly students saying, please help, or I have a test. And we kind of want to downweight those sentences because that does not give us any information about the subject matter. So the TF-IDF helps with that quite a bit. And then on top of it, we throw like a simple classifier, a lot of the time logistic regression, because then we can hand it over to the engineering team or anybody to work with it. We fine-tune results based on classic things, precision recall, F1 scores, and depending on specific product needs. For instance, in some product needs, it was very important to be right. It was okay, like false positives were not okay. So we tuned it towards high precision. And it varies depending on what the knowledge base is being used for. I would also like to mention that transfer learning is not the only thing we use. It's a fairly complex process. One of the things that has been very useful here, and I won't talk about it, but it's weak supervision, where basically you write rules to generate training data, and that's just to augment the small amount of annotated data that we have. On average, we were able to achieve more than 80% accuracy for the different nodes in the knowledge base. And we have just started working with flashcards. In the flashcards domain, what happens is, one of the things we want to know is what are like the dominating topics or dominating themes or concepts that are represented by a term. For instance, if you type cardiac muscle and if you try to search for all the flashcards that are available, you get like a range of topics. Someone will say this is striated muscles of the heart. Then there are other concepts like musculoskeletal. Then some other cards say propels blood. So one of the goals has been to find the number of unique concepts. This is in general not easy because a lot of the times there might be just one card with a different concept, but we try to find the dominating concepts in general. Another thing that I've just started looking at is word sense disambiguation, particularly since the contextualized word vectors promise to work very well in this space. And this again has to do with things like if you search for pleated sheet, I'm not a bio person at all, but my obvious answer was cloth curtain or something in that space, or there's something in dancing as well. But pleated sheet is a regular secondary structure in proteins. So trying to disambiguate these, typically this is not hard because usually a student will come and you can gain enough information to figure out that they want bio, but sometimes there are terms within a subject that can mean different things. So this is fairly important. Another example is circular. It's a mathematical concept, but it's also a store advertisement. It's a direction we are looking at. Another direction that we've started looking at, especially with character embeddings, is extracting equations. So when students ask questions, there will be, and I think it was there in the example as well, that equations are typed in very different ways. So just to find what equations are being represented. It also helps to know, it kind of binds, so equations are there in like online tutoring, they're there in flashcards, tech study, but there's also math solver, so it helps us bind all the products together. And finally, I will say talk about democratizing NLP in phase 2. So with something like the knowledge base creation, we basically tag all the content and we have a structured knowledge base, like basically that's an SQL table that can be queried by anybody. So if someone kind of asks, what percentage of our statistics data is in probability, you can write an SQL query and give an answer. So this makes this information available for report generation, for BI tasks, and others. It's also like this also feeds into building recommendation systems for match. One of the things he said during my introduction was matching tutors and students. So when students come in, they will write the text, and once they're tagged online with what the subtopics are, it helps our recommendation system point the students towards the right tutors. And finally, I think I will reiterate the same point. In real life, most problems are small data problems, and transfer learning kind of replaces feature engineering to a certain extent, which makes it really cool. The other thing that is also interesting when you're using vectors as features is you might have additional features like views, clicks, conversion rates, which could go into the same model and produce something better. So you have the option of augmenting it with structured features. That's it. One more thing I would mention is in NLP, we have not explored like the whole contextual word embedding as much as people have in computer vision. So there are studies, there are papers in computer vision which kind of says like, why does transfer learning work? Those kind of works are on the way, and I think like in a few years, probably NLP will be at a point where it can use like all the context, all the different layers more effectively than what we're doing today. Thank you. Yeah.
So it seems like your entire application is pretty dependent on Elmo, right?
Yes and no. So Elmo, I only started working on it like 2 months ago, maybe. So I mean, we were doing fairly well with in-house built representation of sentences and characters as well. Elmo does improve the process. It's also possible, like if you just look at the Elmo architecture, it's not that hard to write it yourself in Keras and something else. But I wouldn't, since it's already there and it has shown improvements.
Have you looked at BERT?
I haven't. There's also ULM Fit, which is in the same space. And this is also like another direction that we are exploring, that what other packages exist in this space. Yes.
Okay, so you mentioned a couple of times that the data set store that you had, I guess, the corpus is kind of small. What sort of number of words are you talking about?
Oh, the corpus is not small. Sorry, I probably should have. The label data is very small.
Okay,
So the number of data that is tagged as probability is very small. But the corpus is huge.
okay, but so what is the size of that was restrictive to use like a word to vec, like to train a word to vec? Is that smaller number of images?
What's your question? Like what it will?
I'm kind of curious the size of your labeled data set.
The size of the label data is pretty small. I would say for something like probability, which is a pretty large cluster, I would have like 200 to 300, but a cluster like regression would have like 100.
So you were training individual models on each of the clusters?
It was, it's kind of complex. It's not necessarily on each of the clusters. So it would be, sometimes it would be multi-class labeling. So inside each of the clusters, it would be multi-class labeling, but for the level of probability testing and regression, it was against each of the clusters. That's right.
So, forgive me because I'm not exactly sure how Chegg works, but when a student writes an input query, for example, saying I need help with X, is there any aspect that allows you to monitor state in a dialogue? Because let's suppose that query, the response was incorrect and the student wanted to say something else. Is there any
We don't, how should I put it? So you're saying if the tutor did not answer correctly?
Yeah, or let's suppose, for going back to your example about pleated sheet.
Yeah.
Let's suppose the student was indeed looking for.
We do have data on that kind of work where if you were looking for pleated sheet and if you, like there are search logs and things like that that gives an idea of, what the student found and what they did not find. Also for check study where the expert is answering offline, there are measures to see satisfaction of the students. The part where it's a little tricky is where it's online tutoring. Sometimes people are on videos. There's like maybe a little bit of chat, but the chat might not cover the entire content. In that case, we typically rely on reviews, and if the students are not satisfied, typically they'll write a bad review. And you could say like a medium experience is very hard to detect because people don't write a review in a medium experience, but.
So the context you mentioned is just the sentence, the word is in.
Yeah.
Do you find any situation is necessary to consider sentence like next to that sentence?
So that's how I created the sentence vectors. So the skip thought vectors, and I have the architecture of the skip thought vectors in the appendix. But the skip thought vectors basically predict this sentence given the sentence around it. And in the final classification, I've used both the sentence vectors and the context vectors because the context vectors alone did not give as high accuracy than without the sentence vectors. Yeah.
So you mentioned terms that might be confused or have different meanings. Have you given any thought to like groups of terms that might be applied in different areas? Like for example, like PEs might show up in math, they also show up in physics or chemistry.
Sure. What? Oh, okay. So.
Asking, I want to understand how PEs relate to this kind of reaction.
So, so if you look at this knowledge base structure, when I think in this term, we actually classify the data as what subject it belongs to, and then we go and classify underneath it what sub-subject it belongs to. So we also ask the student for the subjects. A lot of the time they're not correct. So we cannot totally depend on it. So we kind of go in a hierarchical fashion. So in principle, we should know that if this is a PD in math or physics. Having said that, a PD in math or physics, a question could be very similar, right? That's possible. In that case, it's very easy to get it wrong. And most of the questions that are not detected accurately are in that very confusion zone where the language is so similar that it's very hard to disambiguate.
So you just pick one particular person and say, now it's probably the right choice.
Yes, yeah. Any more questions?
All right, let's thank Sangha once again.